This is a very beautiful and famous pattern that you're looking at here. It's in the shape of a triangle, and that's what it's called, Pascal's triangle. Pascal's triangle was described by Blaise Pascal, and it has many real-world applications. It can be used for all sorts of different formulas and equations. It's very useful, and it's also fun to think about. What you're going to do with your partner first, you're going to notice at least three different patterns. There's a lot of them. You're going to look for at least three patterns. You'll describe the pattern for the number of terms in each row. So, for example, this row has one term. This row has two terms. This row has three terms. This row has four terms. So that's what you're going to describe, how the number of terms in each row is changing. This part right here. Next, you need to describe the pattern within each row. So what's happening between the numbers in each row? That's what this is asking. So we went 1, 3, 3, 1. What's the pattern within that row so that it goes 1, 3, 3, 1? And then also, how is that related to the row above it, right? So we're going to look within and we're going to look above. Number 4 asks you determine the pattern that results from determining the sum of each row. Remember, sum means to add, so try adding it up. Like 1 is just 1. 1 plus 1 is 2. 1 plus 2 plus 1 is 4. 1 plus 3 plus 3 plus 1 is 8. What would happen if you kept going? That's what number 4 is asking about. There's a lot for you to explore here. And then finally, the 5th one says determine the next two rows. So what would be the two rows underneath that bottom one? Well, this triangle could keep going forever, really. We want you to figure out the next two and explain your reasoning. So this is your task to do with your partner. And I think you can figure all of this out. It's fun to think about. Take it one question at a time. We're going to spend 10 minutes on this task. So set a timer for 10 minutes and pause the video. And then work through this with your partner. While you're working, your teacher will be circulating the room and checking for understanding. You've hit play, so that means you are ready to talk about this. This is fun, so if you're still working on it, hit pause again. I don't want to give the answers away before you had a chance to finish. Okay, here we go. So at least three patterns that you noticed. I'm actually going to come back to that one last because we're going to talk about a lot of patterns that we noticed. Describe the pattern for the number of terms in each row. Well, let's see. The top row had 1. The next row had 2, then 3, then 4, then 5. And again, this is just if we count the number of terms in each row like that. We're just counting the number of numbers in each row. So it's increasing by 1. It starts with 1 and it increases by 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, right? If we wanted to go to the rows beneath the pyramid that we have. The pattern within each row. So it helps to start at the top and work your way down. Oops, let me get rid of that. I'm going to ignore the one at the tippy top right now and just think 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 1 is 3. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. So you can use each row of the triangle to generate the row beneath it. 1 plus 4 is 5. 4 plus 4 is 10. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 10. And then the next row, 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15. 5 plus 1 is 6. And so on. And then the other spaces just get filled in with 1. So we have a 1 at the top and we have a 1 on the left side and the right side of our pyramid. And we could generate this forever. We can make an infinite number of rows of this sequence if we wanted to. To write that in words, I'm going to write down that each value is the sum of the two numbers above it. So that's what's going on. Now let's talk about the pattern that results from determining the sum of each row. Well, the first one is just 1. And then 1 plus 1 is 2. 1 plus 2 plus 1 is 4. 1 plus 3 plus 3 plus 1 is 8. 1 plus 4 plus 6 plus 4 plus 1 is 16, and then our next row is 32, and our next row is 64. So what's going on here? Well, one way to talk about it is to say that we're doubling each time. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. You could also think about it exponentially if you wanted to. You could say 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 2 is 3. 2 to the power of 4 is 16. So there's different ways to think about this, whether you're doubling every row or using an exponential function with a base of 2. Those are really just two different ways of saying the same thing. Let's write it down. Using words, I'm going to say the sum doubles each row. We could also write an equation if we wanted to, using an exponential function. But that's getting fancy, and we haven't really done that yet. So for now, it's enough just to say the sum doubles with each row. Determine the next two rows in Pascal's triangle and explain your reasoning. So now we should be able to do this pretty straightforward. We know we start with a 1. 1 plus 6 is 7. 6 plus 9 is 21. 15 plus 20 is 35. And then it's symmetric. It's the same values going the other direction. Ta-da! Let's just do that one more time. All right, there's my 2 rows. It's getting big now. Now, to explain my reasoning, I'm actually just going to draw an arrow over here to number 3. Because that's what I did. I recognized that each value is the sum of the 2 numbers above it. And that's how I generated those 2 rows. At this point, you're probably pretty familiar with the idea of what a sequence is and what a term of a sequence is, because we've been using those words a lot. Let's go ahead and clarify that formally. A sequence is a pattern involving an ordered arrangement of numbers, geometric figures, letters, or other objects. A term of a sequence is just an individual number, figure, or letter in that sequence. There are 10 examples of sequences in this activity, and they're all fun. For each sequence, what we're going to do is describe the pattern, draw or describe the next terms, and then represent each sequence numerically. I'm going to let you work with your partner to do those tasks for this sequence right here with these plus signs. And what we're analyzing here is the number of dots in each plus sign. We're going to spend 10 minutes on this task, so pause the video, set a timer for 10 minutes. Teachers will be circulating around the room and checking the students' work and being sure that they understand. And if it takes less than 10 minutes, that's okay. Just go and start the video earlier. But hit play when you are ready to talk more about this sequence together. Be sure you've had some time to think about it first. All right, you've hit play, so that means you're ready to talk. All right, so here's the number of dots in each positive symbol here. If I was going to describe these, I would say what's going on is we're subtracting 4 each time. So if I wanted the next term, that's what I would do. I would subtract 4. Could I draw the next 3 figures in this sequence? Sure, I could. So here's the next 3 terms in the sequence. I guess I couldn't go any further than that, could I? Because I'm down to just one little dot. So we've looked at the number of dots, and we've said that it's decreasing by 4. We drew the next 3 figures of the pattern, and at this point, we know if we went any further, we'd have negative numbers. Negative numbers are okay, but we can't draw a positive sign that's made up of a negative number of dots, so that's the end of that sequence as far as drawing is concerned. Represent the number of dots in each of the 7 figures as a numeric sequence. So all that's really asking us to do to represent it as a numeric sequence is just to list the numbers. So instead of drawing pictures, we just make a list of numbers. Let's see, after 13 is 9, and then 5, and then 1. And I'm going to put dots because that could keep going. We could keep subtracting 4 if we wanted to, but then we couldn't draw a picture if we kept going. Let's go ahead and put that in the table. The first term was 25. The next term was 21. The third term was 17. The fourth term was 13. The fifth term was 9. The sixth term was 5. And the seventh term was 1. So there's a value for each term and there's a number for each term. The number represents the position and the value is just the value of the term that's in that position. All numeric sequences can be represented as functions. The independent variable is the term number. So we've been talking about independent and dependent. This is the independent variable. And this is the dependent variable. And the reason they're always functions is because the term number doesn't repeat. Here's another sequence for you to work on with your partner. This time I'm just going to ask you to set a timer for 5 minutes. When you're ready to talk about the family tree, hit play.